So I am actually going to be doing my HackerRank technical assessment today. So I'm trying to get some last minute prep in. And one of the things I'm going to be doing now, and I probably should have done more of this, is the idea of graph traversals. So first I need to set up a good graph data structure, and then I'll go over breadth first search and depth first search, and then I'm going to look at Dijkstra's algorithm for the shortest path. One thing I'm going to be definitely doing is grabbing some information from the internet. So there's this tutorials point website, I think, and for those who aren't too familiar with graphs, so you'll see here that all three of these are actually graphs. Graph number 2 looks very similar to the binary tree that we were looking at before, because binary trees are a kind of graph, but they just don't have any circularity to them. So they have that convenience that if you traverse that tree, you don't kind of bump into the problem of seeing something you've already seen. Whereas like graph 3, for example, this circularity can be an issue that you need to consider when looking at these kinds of graphs. This would be something like, or this could represent something like a location, and like the lines in between, which are called edges, are like distances. So you can imagine, like, how do I get from New York City to Boston, and these are all the different routes and cities that are along the way, and you're trying to find the shortest path. That's a very common problem, and that's what we're going to be looking at today. Let's create our class here. So I hope hope you guys can see that. And I don't need the terminal right now. Okay, class graph constructor. Constructor, and I don't need it to have anything. This dot nodes equals a set. This dot edges equals, and we can use a object literal here. And I want, or I can use a map also, but I think I'll just stick with the lazy object literal, because we're using numbers, so we don't need to have a reference to an object itself as a key. But that would be a consideration if you did want to set up an actual node class with node objects. I don't feel I need to do that, but I have side by side because I'm trying to be faithful to what I'm doing here. I will change some of the naming, so I am implementing it in a slightly different way that I feel is more appropriate for what I'm looking for. So we'll have we have an add node method, and this will be some I'm gonna call it label because it really is just a label. Add edge. This is a bi-directional edge, so I want to be really explicit here. I don't know if I need to be. Directional edge. It's also kind of long, but I'm okay with that. And add directed edge. And there's also this display function, which I think is really cool. It looks awesome. So I'll have a display. So I'm going to be able to add a node, add an edge, both directional and bidirectional. And that is it. Seems pretty simple, right? So let's start creating some stuff. All right. Also, I'd like to make some test stuff first as well. So g equals new graph, and we'll start adding stuff at the end of that. Yeah, I think that's fine. All right, so add node, and this is going to be a label. So what this is going to look like is I'm going to have g.add node, and I'm going to add a node with the 1 as a label. Again, doesn't really matter what these labels are. It's as long as they're unique. This would be 1, 2, 3, 4, 5, 6. I can use letters. I can use whatever I want, really. But I'm going to stick with numbers because I'm lazy. Okay, so we have to add a node now. So how do I add a node? So with the way sets work, I want to add the set. So what's cool is this dot nodes is a set, and you can just do dot add and label. Hopefully you can see that. So I'm going to create a set here. So I'm saying x equals new set. All right, and I can do add 1. Now my set is a set with the value 1 inside of it. If I try adding 1 again, it doesn't throw an error. It just doesn't do anything because it already has that that item inside of that bag. And I want the node to have its own array of edges, and those arrays actually, do I need an array? Because this also like a set of a. I think I want it to be a set actually. Yeah, let's make that a set. But I need to like instantiate it effectively. So if this is a new label, I want to create a edge specifically for that one. So I'm going to actually use this. I think you do x.has. So do you have 3? No. Do you have a 1? True. Okay, so I could use the .has for the set. So this .nodes.has label. So if you already have the label, sorry, I should say if you don't have the label, then add it. And this is going to be this .edges. I'm going to say label. I'm going to equal a new set. Okay, so this is me initializing edge for node. Okay, so I should be able to look at me. I have like all these. I hope this makes sense. By the way, I hope this like isn't too zoomed out. I'm gonna zoom in more here actually, because this is like a lot of stuff. I know. I probably don't need this anymore actually, because it's I have a console here. All right, so what do I want to do? I want to do g dot or console dot log g dot nodes, and same thing for edges. All right, Node.js graph. All right, cool. So let's do add edge. So this would be the bi-directional edge. So here's one thing. I actually want to do the way I anticipate doing this, because I like the idea of like reusing code and being and not repeating yourself, making dry code. I have the idea that if I'm implementing bi-directional edge, I'm probably going to just call the directed edge. So I just, it all lives in one place basically. So that's what I'm going to do. You have node 1, node 2, await, defaulting to 1. So what is the wait? Await is effectively, if I go back to my graph example again, it would be like the distance between A and B. So here's another thing I'm thinking about. I don't so when I say node 1, that's actually like label 1. It's not, again, there's no node object. So I'm also of the I also like the idea of not having to call add node over and over again. Like I just want to like create the directed edge, and it just creates the associate, like it adds the node already. Like I don't need to call add node explicitly. So I think I like that idea. So this will ensure nodes are initiated correctly. Okay, it's okay. I'm okay with the redundancy, because this check will yeah, that's fine. That's a very quick check basically. So let's do that. This dot add node 1, node 2. That just ensures that those are working. And now we will add edge. So I already know for a fact that because I initiated them correctly already, I can just say this dot edges, call node 1, and say, okay, you will now add, because you're a set now, you're adding this object literal here, so that's fine. I'm gonna split up here. So you're adding node equals node 1, sorry, node 2, and your weight, don't like all this like extra information. Weight equals weight. Weight spelled properly. It has a default weight of 1. At this point, I don't really care about adding the weight, but you can definitely tailor that to your needs. Okay. So I want to test this out. I want to see if this works. So I don't need to do the add edge anymore. I could just say add directed edge, and I want to say 1 to 2, and I'm also going to say 2 to 3. All right. So I have my set of 1, 2, 3, and I have a direction of 1 to 2, and also 2 to 3, but 3 has no connection. This doesn't seem right though. Oh, it's a directed edge, so it is 2 to 3 and not 3 to 2. That is actually the point. And we fix that by going at the directed edge. So I'm gonna actually like reduce some of this because there's a lot of clutter on the screen. And okay, cool. So bi-directional edge. So this node 1, node 2, weight equals 1. So here, I already have all the stuff made in add directed edge. I just need to call them 1, 2 with weight. And then again, but this time it's 2, 1. Okay. And I also need to put this dot. This dot. Oh my goodness. This dot. Okay. So now let's add some bi-directional edges, 1, 2, and 2, 3. So here we should definitely see that everything is connected, or all except for 3 and 1, but whatever. Okay, cool. So we have the set of 1, 2, 3 still. We have the edges, which is from 1 to 2, but also now from 2 to 1, and then 2 also goes to 3, and 3 goes to 2. Display. Oh, this is so cool. I love this, the way this display thing works. It's really easy and doable, and I'm going to do it. I'm going to doable it. Okay. Can I move you a little bit? Okay. Okay, cool. So it will establish display. It will establish a graph. I'm going to call it output. Okay, and then it just console.log output. Alright, cool. So it does this node. Well, we do for each. So instead of for each, I'm going to do for, because I'm dealing with a set now, I need to do const node of this dot nodes, this dot edges. So output plus, so I'm going to add strings, this dot edges. So it's going to be node. I'm going to use, you know what? I'm going to use, string interpolation. Oh, ES6. All right. The node, the arrow, and then some more code here, which will be this dot edges using the node itself to access the set of edges. I'm going to do array from, and I have access to the array methods, and I'm going to do a map, and I'm going to map the edge with, or no, that's it, right? I just need the edges. Oh, dot node, edge dot node, and then I could join on parentheses. I think that is it. Oh, plus a new line character. Okay, that's fair. Okay, so there's a lot of stuff. But for the most part, and so I'm going to do, so I don't need this anymore. I can just do dgg.display. All right, let's clear this and run it. And that's what it looks like. It looks so neat. I love it. Let me do one other thing. Console.log. I'm going to put something like nodes, node, like some instructions. Edge 1, edge 2, da da da. Just so it like it kind of explains what's going on. So node, edge 1, edge 2, etc. etc. Okay, cool. All right. Breath first search. All right. BFS. I meant BFS. A node, and then okay, well, Q. I'm gonna use an array just because I'm lazy. And what we do is, well, I put the node in that. we have a visited set. Okay. While queue.length, then you can say, oh, visited. Let's add. Well, let me first pop it off. The node. Ooh, node. Current node equals queue dot shift, which is a DQ. And then you add current node to that set, so we know we visited it before. And we can say, hey, if you're not visited, it's basically filtering what it adds to the queue versus filtering what comes out of the queue, which is fine. That's fine. Okay, what am I doing? So now I need to go through the edges. So I need to first find the edges. And that equals to this dot edges with the cur node. And now I have those edges. I can loop through them. Do they use a? Oh, they inherently use a array, so they don't need to convert it or anything. Actually, I don't think I want to convert it. I think I'll just use a regular for loop. Edge of edges. And here I'll have my logic. If visited doesn't has it. Oh, actually, it's edge.node because this is an object that we're dealing with. This is this thing right here. So it needs to be node, not wait. So it needs to have node.node. If you don't have the node, well, guess what? You're going to be added to the queue. And for my own sanity, I want to actually return visited. Okay. So I don't need to display. I want to do BFS, and I want to console log that. Okay. Let's see what that looks like. Booyah. Errors. And fantastic. Current node is undefined, which is because I left this important point out. Okay, let's go from 1. Thank you. Okay, let me kill some of this stuff. Alright. Show me what you got. Okay, it returned a set of 1, 2, 3, which makes sense because everything is bi-directional. So let's add some stuff that's not bi-directional. Okay, so 1 can go to 2, 2 can go to 3, which means 1 can go to 3, but nothing can go to 4 because 4 has no connection. Right? Okay, good. If I do breadth first search from 3 has no connections, so it only explores itself. Depth first search, DFS, the node. Const stack equals an array with the node first. Const visited. So you always need to have a way of determining if you've already seen a node. So that's why you have to add that. And then I can just do my while loop, while stack.length. So while there's still something in the stack, keep going. I do want to return visited, just so I feel better about me actually doing something. And then I want to pop off the stack. So const cur node equals stack.pop. And that just pops it off the end, whereas shift was dequeuing it from the queue. Grab the edges, and this time we have a little bit more order to how we do things. I'm actually just going to copy a lot of this stuff here. Oh, crap. I want to console log cur node, just so I know that it's going in the order that I'm expecting. And I'm doing depth first search on the number 1. Okay. All right, let's see this. Oh, error. Yes. I used the name queue. It's not a queue, it's a stack. It's going in infinite circles, so something's wrong with I didn't add my edge. That's obvious. Okay. Visited.add cur node. Duh. All right, let's do that again. So this is working as expected. You want to look at Djikstra node. You should have a node 1 and a node 2, and say finding the shortest distance between those two. That's what you're supposed to be doing. So that's what I'm going to do. Okay, we're going to do it. We're going to do a linked list, and we're going to set it up as a priority queue. Class node. So you have a val and you have a priority. So in this case, priority is effectively the distance. The lower the priority, the shorter the distance, and that's why it deserves to be at the top. That's what we're doing. Wait, I'm grabbing linked list. Yeah, I'm not like copying all this code. So this is from my video from before. I need a dot next. Yes, that makes sense. This dot val equals val. This dot next equals null. This dot priority equals priority. Okay, coolios. Otherwise, linked list, I'm just going to copy you. And we're not going to call you a linked list. We are going to call you a priority queue. Yay. That's what you are now. Priority queue, we don't delete. We pop it off of the top. So it's actually really easy to do. So I'm not going to actually commit delete. I'm not going to do this get kth to last. That's not what we're going to, not working that way. That's why it's so easy to work with this. I don't need to do anything too crazy. So this is, okay, I think I can add these things. So these are fine. These are the basic functionality of this priority queue. I don't need the print, and I think this is fine. I don't want to have it start with anything. So your root is null. Okay, priority queue, you have some simple things going on. So is empty, fantastic. All right. So are you empty? Oh wait, are you empty is negating. Are you empty? Yes. So root is null. It becomes true. Okay, cool. I'm gonna call this peak front. Where's peak? Peak front. Fine. I'm gonna put you up here, so that's easy. Peak front. This will be return this dot root dot val. That's it. If you're empty, then throw an error. Priority queue is empty. All right. Enqueue, which I'm calling append. So it needs an item, a value, or a priority. Okay, so let me just toss this down here. All right, cool. So we add a. Should I call it enqueue? I think I should call it enqueue. Fine. It's more of an insert. I'll call it insert. Okay. Insert val priority, and then you give a new node the val and the priority. So if this dot is, if you don't have a root, I should say if this dot is empty. You should use your methods. You made them. So here's this is the empty situation. Empty root. I want a situation where root is lower priority. I put lower in quotations here because it's lower in number technically, but lower in priority in the sense that it's going to the back. Use lower in priority, and then need to find spot for new node. node in list. Now that I think about it, this is called a priority queue. So maybe NQ is right. Okay, so if root, so this is a very easy situation too. If this dot root dot priority is less than, sorry, if val is less than this dot root priority. Sorry, no, it's priority, the current priority. If you're less than the root's priority, well, guess what? You are the new root, and you can say new node dot next equals this dot root, and then this dot root equals new node. And I will call this a return here so that we kill it before it goes anywhere else. Okay. And then you define a spot. So then you start at the current, you say this dot root while current is next. Here we have our logic, and it's basically similar logic to this. So in this case, it's the current priority. So if current priority, so what I need is the cur.next. So when that's true, then I actually want to stop. Then I want to break, yeah. Otherwise, current.next. And then I know that my cur, so I need to keep track of my next node. I need to keep track of my dot next here, because I'm going to be swapping it out, because cur.next is now equal to the new node. New node dot next is equal to the next node. And I think that is it. We have to do some testing here, of course. So DQ. Okay, DQ is super easy because it is straight up from the so remove top node. So say the val. So this is the output equals this dot root dot val. And then this dot root equals this dot root dot next. And again, similar situation here as up here, where if it's empty, we don't want to DQ. Then we return output. Okay, that is good with me. Let us check out the priority queue as an object and start making some stuff. PQ equals priority queue, new PQ dot NQ. We need a array buffer view. What the heck are you talking about? Okay, let's say 1 1 PQ dot root. Oh man, all this testing. Okay, that took longer than expected, by the way. Priority queue. I see 9, then 8, then 7, which is proper here because of the priority, because it has the highest priority. If I change this to like 78 or 778, then 8 should be on top, and the last one should be 9. Whatever, but the priority is a 1. Then I should see that crazy value, right? Let me just, it's also like relative, right? So I can do like 2.4, 2.5, and squeeze it between 8 and 7. And sure enough, it goes in between 8 and 7. Cool. DQ. I just take off the top. So now the first one won't be 8, it'll be the big number that I just added here. Okay, so this looks like it's working, and give you some exports. Alright, so all this just so I could get access to Djikstra using a priority queue. Yay! The distances is something I'm going to keep, because I think that's what I'm going to need to know. So let's say let distances? No, you just const distances. So priority queue. So this is my queue. Priority queue. New priority queue. All right. And set distances to all nodes to be infinite except for the starting node. My goodness. Okay, so starting node. So I'm gonna be more explicit here. So this is start. This is the end. Okay. So we set up. We initialize start with 0 priority. Okay, and that's what we do. We do queue dot enqueue. We have the value, which is start, and we give it a 0 for priority. So it is in the system. Then we initialize all other nodes with infinite priority. Let's go with the for loop here. This is for edge, no, not edge, node of this dot nodes, and that is a set, so that will give me a single node. If node is not equal to, if node is not equal to start, then that's the one we're interested in. We want to queue dot enqueue. Oh my goodness, who would have thought these words? Maybe I could do. I'll use PQ actually. That's what they use. I'm gonna use PQ as well. I'm not about to do that all day. Okay, PQ.enqueue, and we enqueue the node with infinity. In capital infinity. Okay. Capital I infinity. Because you'll need to know what the last const prevs called prevs. So this will store each node's previous stores a reference to each node's previous node, to the previous node before previous node, which is the value, before each node, which is the key. Okay, that's me being really so one thing I'm definitely trying to do here is be explicit just for my own sanity and making sure that I can look back at my code and say, oh, I know what this is doing and why. Okay, so prevs. So it looks like when they initiate their nodes within the priority queue, they're also messing with this prevs because there is no previous, so that's why it's set up like that. So prevs node equals null. So there's no, so priority and no previous load, the previous node. Okay, cool. So that is that. Yay. And then we just do our Djikstra stuff. So this is where things are actually the logic, the algorithm. That's what Djikstra. I'm actually feeling a little sick today, so so I've been coughing. All right, let's get this out. This is nailed out of the park. Let's be done with this thing. All right. So while loop, while my queue, so not empty, PQ is empty. This is a method call. I could also make it a getter, but it's fine. Let min node, which is the current minimum node, pq.dequeue. Makes sense. Let cur val, because this is the value of it. This is min. Okay, so their wording is a little weird for me. So this is my current node. This is the value of the current node, and this is the priority of the current node. Okay, I'm gonna let this ride, but I might clean this up a little bit later. Cur priority. Okay. So hold on. When I dequeue, this is important. I was questioning this. So when I dequeue, I don't just return the value. I need to return the actual node itself. So that was here. So I don't return the value. I actually return the node. Okay, so that's literally it. And that's node, next, and priority. Okay. These values are not changing. Yeah, I think it's another const. Edges, which equals this dot edges, and we're looking at the cur val. Okay. So it makes sense that they called it the cur node, because the node is the value is like the label effectively. Okay, I'm gonna call this node object. That is what it is. This is the node, and this is the priority. Makes it super clear. Okay, that's nicer, I think. Okay. And this needs to be node object. Oh. Copy, paste. It's hard, you guys. Okay. Ugh, I'm dying over here. So for const edge of edges, now we can look at this alt. So let const alt. Const, I'm going to call this like possible distance. Possible distance, yeah, fine. Equals distances, node, current node, yeah, node, and then plus neighbor weight. So hold on, that's the edge, and in this case, it's the edge. It's the edge dot weight. So you're saying, look at the current node's distance from the start. Add on the neighbor's weight, because that gives you like what what moving to that node would look like. And then you say, okay, this is my condition. If my possible distance is better than my neighbor's current distance, so this is edge.node. So what does that look like? So if my neighbor takes longer, then I want to... you're looking at your neighbor's node. Oh, you're updating your neighbor's node. I see. Distances, and it's the edge dot node. So I'm gonna I think I'll be explicit here and say this is the neighbor. I'm okay. Oh yeah, the whole point of this is like to learn, so I'll call it neighbor. Neighbors. Yeah, I don't want to confuse the priority with the weight, so I think I'll just call it neighbor dot. Neighbor, copy pasting. Neighbor dot, neighbor dot, neighbor dot, and that is equal to the possible distance, because it is better now. Then you check your previous. You check out your previous neighbor dot node. You set equal to the current node, which is just node. And now, fun part where you actually add to the queue again, and queue. And remember, it adds to the top if it's a higher priority. So you are now looking at your neighbor node, because that's like the next thing. You're basically traveling through your neighbor, the short distance neighbor, shorter distance neighbor. Oh yeah, yeah. You only travel to the neighbors that are shorter than the shortest distance, basically. Distances neighbor node, which is the same thing as the alt. So why not just put the alt? Why reference this? Why do a call on the function or on the object? Just do alt. Just do possible distance. That is the new weight effectively for that edge. Okay. And then you return distances. Okay, I'm interested to see if this works. I am okay, preps. Priority not used. Good point, because wait, when do I've established a function, a variable that doesn't need to be established. Only the neighbor's weight matters. Okay, cool EOS. Now let's do some Dijkstra's. Oh yeah, I didn't find the end, right? So what do I do? You're supposed to go through the whole thing. So end is literally distances for the end. It's that simple. So maybe let me just see what just the old distances look like for now. I did not add any weights onto any of these things, so I think let's see what that looks like without anything, and check it out. So nothing. Let me return PQ for a second, just see like if it's working at all. PQ has a root of null because I DQ'd it to death. Makes sense. So let me here. Okay, so we have 1 to 2 and so on. Priority is 0. Where do they get priority 0? Oh, for the start node, right? Okay. Nan. Okay, there we go. So what is your weight neighbor? Neighbor.weight. You're not neighbor.weight, you're neighbor.priority. Haha. Okay. Oh, okay. I'm so silly. You don't enqueue. You just give them the distances that are infinite. Okay, that was a mistake. So distances of the node are set to infinity, and then the and then the queue starts out with the start node. That makes freaking sense. Okay. Let's see what we get. You get stuff with infinity. Where are you coming from, neighbor? Neighbor is from edges. Edges does have weight. Sorry, that was a mistake on my part. Still nan. Well, you know, one of these days I'm gonna actually do this right. Okay, seriously. Okay, so let me NQ start and distance start. Start. Okay, how about now? Oh my God. Oh Jesus. Look at that. Okay, so I'm gonna review like what the heck just happened and what is happening. So getting from the start of 1 to 1 is it takes 0 distance to get to 1 because it is the start. And then if I want to get to anywhere else, I actually know the distance already. The algorithm worked to determine that. And the way this would work is I would literally just put end here and just call on the object to get the return value here. So if I want to go to 1 to 9, what distance would that take? 2. Why do I need this prev? Where does it even show up? I could set you to null, that's fine. And then previous node is there. But like, what is it? Is it even doing anything? Well, that's really cool. Actually, it goes through the order. So actually, I want to go through this to get even a better understanding of what's going on. I'm going to plug these in. So I'm going to do this here. So these look like they're all bi-directional. They're also using letters. So I'm going to showcase that this will work no matter what. So A to B has a value of 7. So you see A to B, that's 7. So that's why I'm doing it that way. All right. Oh my goodness. We're supposed to get 9, it looks like. Shortest distance from A to all of these is that. Okay. All right. I can't wait. E is 9. Oh my goodness. It worked. Ah! I am making this video entirely too long. I hope this was helpful, and I had fun making it. And I will see you in the next one. So bye.